All right, so on the topic of linear approximation and linearization of functions, I want to discuss some applications. Where do we use this in the real world? So as an example of this, I want to talk about something called first-order optics. Optics is like the study of light and lenses. And so take, for example, people who want to design like contact lenses, right, for correcting vision. So the way our eyes work, right, is light bounces off objects and enters your eye through the pupil, and then your brain senses it on the back of your eye, and so on, right? So say you have a point that you're looking at. Generally, the points that you're able to focus on are pretty far away. Like here, I'm putting my hand in front of my face. I guess you can't tell that. But if I get way down here and like stick my hand in front of my face, I can't really focus very well, right? Generally, your eyes are designed or evolved to like focus on things that are far away from you. And so if you have an object that's far away, let's take a point on an object far away, light's going to bounce off that point and it's going to come into your pupil. Your pupil isn't a single point. Your pupil is a hole, right? So, but it's pretty small. So the light bouncing off this point is going to enter your pupil, or the lens, if you put a lens over the pupil, it's going to enter along different rays coming out from that point, right? However, because this distance is very large and the like height of your pupil is comparatively very small, the angles at play here, right, whether up or above or below horizontal, that angle, let's call that theta, is very small. It's close to zero, possibly positive or negative, but it's close to zero. So, for lenses, we really only care about angles theta close to zero, right? Any angle that's like far away from zero, we don't really care about it because you're not going to have you're not going to have that happening unless you're talking about a point that's really close to your eye, and we're not going to focus on those points anyway. So, so that gives us a nice like range of values that we care about. It's only some numbers very close to zero. And now, since your eye is spherical, so spherical eye, as you can probably guess, and the fact that this is points radiating out from a single point here, both of those things mean that this is going to involve trig functions. Right, I'm not going to get into the weeds. I'm actually not I'm not an expert on optics. So I'm not going to get into exactly what the equations are, but you can, obviously they're going to involve trigonometric functions, right? So what physicists do is they linearize sine and cosine at x equals 0 to make all of their equations easier to work with, okay? It simplifies all of the equations of optics into things that are much easier to work with. Because you don't need to use sine and cosine. You don't actually even need to use the sine and cosine functions at all if you only are dealing with angles very, very close to zero. You can linearize them instead. So pause this video and take a few minutes to see if you can figure out how to linearize these functions. We want to take sine of x. So for one, we'll call it f of x equals sine of x. And so for the other, we'll do f of x equals cosine x. And we're going to linearize at c equals 0 in both cases. Okay, this is basically like two problems. And think of this as just two homework problems. Pause and see if you can figure that out. We're looking for the linearization, L of x, for each of these. All right, now I'm going to go over these now, hoping that you've paused and tried it yourself. So first of all, we're going to need derivatives. So recall f prime is cosine of x, and for cosine, f prime is going to be negative sine of x. And then also recall that the linearization formula, let me put it at the bottom here, L of x is f of c plus f prime of c times x minus c. That's your tangent line equation. That's the linearization. So let's see. For c equals 0, sine of 0 is 0, and cosine of 0 is 1, right? So we're going to use both of those pieces of information. And so for our first one here, for sine, L of x is going to be sine of 0 plus cosine of 0, so that's the function, plus the derivative of that function times x minus 0. Okay, that's the linearization, and that is just equal to, what's that going to be equal to? Sine of 0 is 0, plus 1 times x minus 0. That's just x. So this gives us the linear approximation. Sine of x is approximately just x. And for cosine, do the same thing. We're going to do the function f of 0 is going to be cosine of 0 plus the derivative, which I'm going to actually write minus sine of 0 times x minus 0. And in this case, since sine of 0 is 0, that term is gone, and we just have cosine of 0, which is 1. This is just 1. So now we have the linear approximation cosine of x is approximately equal to 1. And so what they do in optics is they take their equations that would normally involve sine and cosine, and they just replace sine of x with x and cosine of x with 1. And that's it. And then it simplifies all your equations, right? And then you have much easier equations to work with because you're taking advantage of the fact that these linear approximations are going to be very accurate as long as your input, your angle is close to 0, the point where you did the approximation. So that's called first order optics. And that's because it's using linear approximations, which is a first order approximation. When you get to Calc 2, you will learn about something called Taylor polynomial approximations, and you'll learn about, which is based on an idea called a Taylor series. A Taylor approximation is a way of doing a polynomial approximation of some function. The linear approximations that we're dealing with here, these are first degree polynomials. So this is called first order Taylor approximation. You can also do approximations with like second degree polynomials, the quadratic polynomials, right? You could also do third degree polynomials. So besides first order optics, you also have second order optics or third order optics, which is where you're using like successively higher degree polynomials to approximate the trig functions. And the higher degree polynomial you use, the more accurate your approximations are going to be. So if for some optical applications you might need, might be working with larger angles, and so you might be, you might need to get more accuracy in your approximations, and so you can increase the degree of the Taylor polynomial approximation and get a better function. But it is going to make it more complicated because obviously the higher degree, the more complex your function ends up being. So yeah, that is a cool application. I also want to share with you a story, which is I had a student back in Michigan who had worked in a factory, and he actually taught. He was an adjunct instructor at the institution where I was working, Lansing Community College. And he taught in the tech careers area, teaching topics about like factory, robotics and that kind of thing. And so he was telling me that for factory robots that doing things on the factory floor, the way they program the robots is they actually take some of the equations that the robots need to calculate. So imagine a robot needs to take some measurements and then do a calculation on the fly in order to determine where to weld these two pieces together. Like it needs to be able to take some, sense the position of the thing, of the thing it's working on, and then put its arm in the right place in order to do the task it's trying to do. So robots are constantly taking measurements and doing calculations as they work. And so to program those robots, they actually use some reasonable linear approximations for some of the equations that the robots need to solve. And replacing the complicated functions with the linear approximations speeds up the calculation process, like the actual amount of time it takes to run the program. It speeds that up just barely enough so that when repeated over and over and over again, or over the course of a long time, it does have a significant impact on the speed at which those robots are able to work, and therefore the output of the factory. And so I think that's incredible that it's an example of this tiny, tiny incremental change, right? Where you just make the function slightly easier for the robot to calculate, and it makes the program complete a little bit faster. Where if you just ran the program once, it would be completely negligible, right? You would not care. It would not make a big difference at all. But when repeated over and over and over again, those tiny, tiny incremental improvements add up to like what ends up being a significant improvement in productivity. I just think that's a super cool story. I love to share it with my classes when I get to this section. I don't have like any like math to write down, but yeah, I think that's pretty neat.